Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 OS. It's on GitHub. It's a OS written for stream. Uh, it has, support like boots. It has like memory allocation. It has like Rust async await. It has serial logging, unit testing, RTC, PCI, Ethernet. It's got like peripheral support. It has like some sort of network stack. And like a little bit of graphics and like input handling. So we have like a demo that runs when we launch the OS. Here we're launching it in a virtual machine. Theoretically, it might boot on a real machine, although it probably makes assumptions about peripherals that are hard-coded in QEMU right now. But when we run it, we see like we get some logs coming up. We have some like notes that we have like heap allocation. We have like proof that we can read right to the clock. We're like reading from the Ethernet card. If we like type to it, we have this like echo server up, so we connect to it over TCP, and I say like hello, and I get back like hello, so it sends it back. And we've proven things like HTTP servers, etc., etc. And we have like this little game that we wrote last stream, a little brick breaker demo, so I could like move the paddle around and like try to like hit the bricks away. Nothing too crazy. And this is all fun. And what I thought I wanted to work on next is the idea of like multi-core. So right now, the way we're doing multiple things at once is we're using Rust's like async framework, I guess is like a way to put it. So here in our like kernel, we have this like demo function, which is somewhere function demo, and this sets up like a bunch of different async tasks. So it has like this UDP sender, this like TCP echo server, this like TCP service loop, this like Ethernet service loop, and like our game service loop. And all of these guys get pushed into like this executor where he basically says like, I'm going to put all of these guys together and I'm going to like poll each of them and see if there's any work to do. And if there's no work to do, then I sleep for a little bit. I like turn off the CPU and wait for an interrupt. And then I'll like do these. So these guys are all kind of, they're written to look like they're normal code, right? You have like a loop and you do some stuff, but really it's these like state machines that are polled by Rust's future system. And what that means is we're never really doing two things at a time. On like a traditional single core system, you're also never doing two things at a time, but you're like context switching between threads, kind of like preempting them. Here we're like doing cooperative multitasking between our different drivers. Where the drivers say like, hey, now is the time where you're okay to like stop running me and like look for something else to do. So all that's working fine. But the problem is we've made like a bunch of assumptions that only one thing actually is happening at a time. And we've kind of like taken some shortcuts to take advantage of that. And what I want to do is I want to eventually turn on the other CPUs. And I want this like loop of things that are happening to kind of actually be like kind of spread out across the CPUs, and they can pull work as they see fit. So the way it looks right now is we kind of have like big task, and inside he has a bunch of like smaller tasks. And we kind of just like point here, and we every once in a while say like, hey, is there work to do? Is there work to do? Is there work to do? And when we find that there's work to do, we pull this guy, and he goes like, is there work to do here? 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 And each of these guys might have like smaller subtasks between them. So you have like this like tree of tasks. So the first thing that we'll want to do, or one of the things that we're going to want to do, is we're going to want to split this up so that we actually have like, instead of one task that holds them all, we're going to want like a bunch of tasks in a queue of some sort. And if these guys have subtasks, we kind of want to like actually put those in here so that they can be done by like what just happened? So they can be done by another core if possible. And then once that's done, then this one like resolves or something. And maybe the idea is that we'll have like a bunch of tasks to do. And we'll have like our like 4 CPUs or something, right? We'll draw them in like red or something. We'll have like our 4 CPUs. And they'll just like take work as they see fit. So while this guy's doing work, this guy will take this one, this guy will take this one, this guy will take this one. And then whoever finishes first will take the next one, right? That's all great. So there's some like work to do in order to like split up our like giant work tree into like bite-sized chunks that the CPUs can pull off as they see fit. We need to do some work for like all of our like synchronization primitives. They kind of assume that we're not doing multiple things actually at once. So our like mutex, for example, he just like has like a normal integer inside of him. Like he just has like a count of who's using him. And then he's like, all he does to acquire the mutex is he says like, is my count 1? If it is, that's great. We can lock. Otherwise, it's unlockable. Or we can't lock it, sorry. So something like this is going to have to be like changed to use atomics. We have the idea of like our logger, for example. His synchronization primitive is only disabling interrupts. Because he says like, well, nothing can actually be happening 2 times at once, except for the fact that like the only thing that could interrupt me is like an interrupt itself. And so we'll just turn off interrupts and that will be our synchronization primitive. That no longer holds true if we have multiple threads, or if you have 4 threads pushing or 4 cores pushing to the same logger. Just disabling interrupts isn't enough to like not corrupt state, because like 2 cores might be trying to write to the logger at the same time. So there's a few things that we want to do here. One, we want to like evaluate usage or evaluate sync implementations. So in Rust, the way that you are allowed to use things from multiple places at once is by having this thing called like interior mutability. So you can like say, I have a reference to myself and you're not allowed to write me, but I have this special type that like overrides that, like a mutex, right? I lock my mutex and all of a sudden now I can write stuff in there. And a lot of these guys require sync, like this attribute sync. So if I want to put something in like global memory, it has to have this like sync attribute that says like, not only can you use me from as writable from like 1 thread, but like if multiple people have handles to me, then like they'll do the correct thing. So we have like these ways that we say like, okay, we have done the work to make this thing sync. So I think there's like a sync in here, or maybe it's in interrupt guards. Unsafe impulse sync. Here we go. So here we have like for our interrupt guard, we say like this thing will be synced now. But it's like only true in the context of a single thread OS. And if we actually tried to use this as synchronized from multiple cores at the same time, it would like start to have undefined behavior. So we have to go through and look at all the places we've written this and see how we need to change those to make them work correctly for multi-thread. We also will eventually have to look at our future executor. Should support smaller chunks of work. And we also need to support like multiple future executors at once. So if I look at like my future executor, it's using this like static variable that is changed from within interrupt handlers to tell us if we have work to do. So the idea is we have like a future where the future is like basically like a thing that you poll every once in a while to do work. And if he says like, all right, I'm not ready to go, nothing to do, then what happens is we go like, okay, well, there's nothing to do. I'm just like going to take a quick nap, right? Turn off my CPU, run a little halt. And when like external hardware, like the Ethernet card, like it receives an Ethernet packet, or like the keyboard keys are pressed and like user input has happened. An interrupt fires on the CPU, so it kicks us out of here, and we like go into like this other area of code, and it runs like an interrupt handler. And that interrupt handler needs to say like, okay, you should like no longer be sleeping now, CPU. Like, do some work, please. And right now we're doing that with like this like static boolean, but that assumes that we are only running like one executor or one future. And if we were trying to run like this, if we were trying to like run futures on like 3 or 4 threads at a time, one, we wouldn't know like which future is correct, like which future is ready, and we also wouldn't be able to distinguish like this like flag is like not for a specific future or a specific executor, it's for like everything. And so there's like an assumption here that we're only running in one at a time, and I haven't really thought too hard about like what that means in terms of like how this would function. I think probably what's going to happen is we're going to have a like a wake up mechanism per future or something that we put on the executor, or maybe per executor, not really sure. And the interrupts need to have like a way to communicate with those things. So I think one of the things that I've already thought about that I like for sure want to implement is the concept of a like how do I call this? Lock-free queue. So one of the like problems here is the reason that we're using this interrupt guard as our synchronization primitive instead of a like mutex or something is if I have like the mutex locked in my normal code and then interrupt fires and it tries to like push to the logger and it needs to lock a mutex. If I'm already in the logger and the mutex is locked, that's like a guaranteed deadlock because the interrupt handler, like if he tries to wait on that mutex, he goes like, is it ready yet? I'm just going to sit here and wait. Because it's in the interrupt handler, the other code that it needs to unlock it will never run. And so we like solve this with interrupt guards where we say like, just turn off interrupts so that we can't interrupt ourselves. We can't like get into that state. But that's no longer valid because like multi-CPUs might be working with this as well. So what we actually want is like a lock-free queue. So the idea is that if it's lock-free, each like user of this queue can start pushing in data simultaneously. And then you can like, how do you say this? Simultaneously and sorry, brain's melting. Each user can like push data simultaneously, and then you just update the pointers atomically, and there should be no waiting. Yeah. So I think that's the first thing I want to look at because I know that we're going to do that. It's at least for the logger. Instead of using like a synchronization primitive around the circular array, we're going to create like a lock-free queue, and that's how we're going to push messages to the logger. Yeah. All right. So let's think about this. So that's intro done at like around 12:50. Okay, so let's go to utils and let's make like a module for like lock-free queue. And we'll edit this. We'll go edit source util lock-free queue rs. And what is he gonna have? He's gonna have a struct. Maybe like circular. This is going to be like a circular buffer. The same way we had like a circular buffer before for the logger, we still want a circular buffer. So the idea is that we have this like memory that's kind of like in a linear memory, right? That'll be like pre-allocated to be a certain size. Maybe you could like handle reallocation in here. I haven't really thought about this yet. The simplest case here is single. How do I say this? Like predetermined size. And what'll happen is, as we are inserting data, we're gonna have like a head and a tail. So the idea here is everything in here is valid data. And when we insert data, we will insert it here and then increment the tail, right? Then eventually what's going to happen is we're going to get to the end. And so we're going to like pop stuff off. So eventually our head's going to move over here. And this stuff will be marked as invalid. And the tail will like wrap all the way around. So he'll, set all these guys to valid data, wrap around here. And sorry. Right, then we'll like have like head, tail like this. So all of these will go bump, 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 then wrap around. Great. Now The tricky part is like, how do we get data in? So let's replace O's with X's. These. Replace O with X, all of them. There we go. So you'll have like your head and your tail will be matched up in the case. So let's pretend there's like one valid element in here, just to make it easier, or maybe a couple. So we'll have like our tail here, and if we try to insert two elements at once, we kind of have to like mark that we're going to put stuff here without actually putting it there. So I think what we actually need is like a second pointer. So what'll happen is like we'll bump one, and we'll say like, hey, I am going to write to this guy. So here is the valid elements. Here is the like reserved elements, and here's are invalid. And so then what'll happen is if two guys are trying to write at once, we'll get like two reserved, and then somebody else, like this guy, will be bumped down here. And then what'll happen is both of these guys will try to put their elements in parallel, and then this other, like the actual thing, will get bumped as they move up. We're also going to need to like handle the case where maybe like the second guy is faster at copying his memory in for some reason, or is copying his element in. And so how do we handle like if this guy gets completed, then this guy? What'll need to happen is we'll need to bump this, the like tail pointer, the valid pointer, as like from when we move from this state to this state, where we go from like uncontiguous to contiguous ready. Somebody will have to like check every element and bump accordingly. Like at some point we'll have to jump over all elements in a row that are valid and reserved, I guess. So yeah, that's kind of like the plan. And let's kind of like start looking at what that looks like. So we'll say the backing data, we'll probably just make an array, right? So this is the size of the array is in like part of the type. Then in here we're gonna have what? We're gonna have like struct, or elements is gonna be an arbitrary type with n elements of it. Then we're gonna look at we're gonna need like the head is going to be an atomic usize. So we need to use core sync atomic, and then we are going to need atomic usize, and I know that we're going to need ordering later, so I'm just going to import that now. We need to throw these guys in here, TN, like this, and probably here we need to say that this is a usize. Great. Atomic usize is to have like the correct name on it, and we're gonna have like a head, a tail, and reserved, I guess. So head is where we can pop elements from. Reserved, I guess we'll go in this order. Tail is the last valid element in the buffer, and reserved is going to be first valid push position, right? As we said here, there's going to be, you know, some people who are writing in parallel, and then some people who, like, this is going to be the one at the back. So when we push, we're going to push an element, type T. We have some, like, we're going to steal some this function from the circular buffer implementation. This like wrapping, we already have a circular buffer that's not atomic, so we're just going to, we might actually end up just fully replacing it eventually, but we're going to steal some of the details from it with this wrapping increment is one, where we increment our element by 1, and then if we hit the end, we wrap back around to the beginning. So the first thing we're going to have to do is we're going to have to increment the reserved pointer. So here we're actually going to take in atomic usize. Maybe. Well, let me think. Okay. So the first thing we're going to do is we're going to... Let's start without wrapping for now. And we'll move into the wrapping version later, because it'll be easier to think about that way. So... on push, we're going to say that the tail is going to have to be incremented by 1, but later. The reserved is the first thing we're going to do. We're going to reserve a spot. I don't understand why my language server isn't working. That's kind of bothering me. 1 sec. Let me just restart my editor real quick. Yeah, I don't understand why it's not auto-completing. That's annoying. Oh, there we go. Self.reserved. I guess we can just fetch add 1. So adds the current value, returning the previous value. No. I think that I don't actually want to do that. So if multiple people are trying to do this at once, what's going to happen? We're both going to try to increment. So we're going to say, what's the load, I think is the way to get the value? Reserved load. And I think that we want to have the acquire ordering. Let's look up the atomic docs really quick. I forget this every time. So atomic usize on the Rust docs. I guess ordering is actually what we want. This one. So there's relax, which means we're going to guarantee that we write the memory, but we don't actually know what order. Release, when coupled with the store, all previous operations become ordered before any load of this value with acquire or stronger ordering. So all previous writes become visible to all threads. Great. Acquire. When coupled with the load, if the loaded value is written by store operation with release, then all subsequent operations become ordered after that sort. Great. So that is what we want. And then acrel is just a like let's see. No, it's like the two combined, like so it's just on stores it's release and on loads it's acquire. But it is saying that in the case of compare and swap, it's possible that the operation ends up not performing any store and only has acquire ordering. That makes sense. Because the swap might not happen. And so this is an additional guarantee that all threads see sequentially consistent operations in the same order. So I guess I don't really understand what the extra constraint here is. Not only order memory the same way as release acquire ordering, but everything that happened before a store in one thread becomes a visible side effect in the thread that did a load. Oh, okay, so I don't actually care about that, right? I only care about like the atomics themselves getting the right order. I don't care that like everything that happened before the atomics store is in the right order. I think. Maybe I do when I pop elements, but I think I don't. This is only for reserving a slot. And so all I care about is that the index is correct. Okay. So here we're going to load the index. So we'll say push index is this. Then we want to try to increment this, right? So we're going to say self.reserved.compare. What's compare and swap versus compare exchange? So this is, they don't like this instead. They don't like compare and swap anymore. Probably. Why don't they like this? Compare and swap is equivalent to compare exchange with the following mapping for memory orderings. Compare exchange weak is allowed to fail spuriously even when the comparison succeeds, which allows the compiler to generate better assembly code when the compare and swap is used in the loop. Sure. Compare exchange stores a value into the topic integer if the current value is the same as current value. Great. That's good. The return value is a result indicating whether the new value is written and containing the previous value. On success, the value is guaranteed to be equal to current. Great. Wait. No. Don't I want success? This is guaranteed to be equal to new. 5, 10. 5. Oh, because maybe, I guess the return value is the old value. I see. So they give us back the old value, and then it only succeeds if we inject the new value, probably. Yeah. So I guess I want to see the guarantees of fetch add, because if fetch add is called by 2 threads, if that guarantees that they get 2 unique numbers, then fetch add is good enough for me. So as the previous value, return the previous value. This operation wraps around overflow. Fetch add takes an ordering requirement, which describes the memory ordering, blah, blah, blah. Yeah, that's not clear to me at all. Not clear. So, also, fetch add is not good enough for me because I need a I'm going to need to do like a wrapping add on the new index anyways, right? So I'm going to do let wrapping increment push idx. Here, well, we're actually going to change this signature to return a usize. And we're going to say that the new tail or new reserved is a wrapping increment of the index we just had with size n. And I wonder if you can actually, maybe it actually makes sense to parameterize this as with a constant, because we know that this is going to be a constant at compile time, so we can maybe get better code by doing this. Which is kind of cool. Okay, now what we're actually going to do is, in a loop, we're going to try to compare exchange. The current value should be what we got back. The new value is new reserved. On success, the ordering is ordering. I think we just use acrel for both. But I actually should double check what the different orderings here are. So failure describes the required ordering for the load operation that takes place when the comparison fails. Using acquire as success ordering makes it so that the store part of the operation relaxed, and using release makes the successful load relaxed. Whoa. Success describes the required ordering for read, modify, write operation that takes place if the comparison with current succeeds. So we load the value, but we don't know what ordering we're going to use to load it, right? Let's think about this. Success describes the required ordering for the read modifier operation that takes place if the comparison with current succeeds. Failure describes the required ordering for the load operation that takes place when the comparison fails. Using acquire as a success ordering makes it so that the store part is relaxed, and using release makes the successful load relaxed. The failure ordering can only be exist, acquire, or relaxed. Oh, okay. So I guess on failure, we're not writing anything, so acquire is reasonable here. And on success, we probably want acquire. No, we want release. But that doesn't sound right. Using acquire success ordering makes the store part of this relaxed, and using release makes the successful load relaxed. So I don't understand why don't I want the load to be acquire and the store to be released? Don't I want both? So maybe I just write acrel or like this one. And on failure, we don't care because we're not storing anything. That seems pretty reasonable. Can I use acrel for both? The failure ordering can't be acrel. Okay, but the success ordering can. Okay. That seems reasonable. And if okay. So if this succeeds, we break. Otherwise, we try again, right? That seems reasonable. And the linter is telling me that I probably want this to be is okay. Like this. All right. Now the problem is we need to get these guys out. So we actually probably want like let mute push idx, let mute new reserve like this. Actually, we only care about the push index. There we go. Oh, and then we say push idx equal this. Okay. Cool. So I think this is right. I think that we'll only get a push index that is valid here. So let's just think about this again. We're going to load a value with acquire ordering, which means that it's going to happen after all stores with release. We're going to try to increment it, and then we're going to try to store that incremented value back. And if we fail to store it because somebody else has incremented again in front of us, which is only going to happen but with this store from the compare exchange, we go again. Otherwise, we break. Perfect. We have a push index now. Now, we try to put the element in. So we say elem push idx is equal to elem. Now, there's an obvious problem here. This should be elements here. Elements. Self.elements, actually. Now, the obvious problem here is that this is non-mutable. So this has to be behind an unsafe cell, actually, which tells the compiler, hey, we might change the shit in here. Or this is a cell, unsafe cell. Although I'm not sure what the rules are about if this unsafe cell is allowed to be written between multiple threads. So let's look at this unsafe cell. I think I saw in here, I saw sync unsafe cell. But it implements sync if T implements sync. Unsafe cell doesn't implement to sync. To prevent accidental misuse, you can use sync unsafe cell instead of unsafe cell to allow it to be shared between threads, if that's intentional. Providing proper synchronization is still up to the task. Sure, so it doesn't matter. It's just like a sync. It's got a marker on it. So probably what's going to happen is this is going to be an unsafe cell, and we're probably going to have to insert like a memory barrier after store, actually, which is probably where the seqcst ordering comes in. But I think we don't have to worry about that on push. So anyways, we have this unsafe cell. We're going to say that like we are now confident that we're the only accessors of this part of memory because we have like our we've got our reserved thing moving up atomically. So this is synchronized. And here we can just say dot get. I think we can like do this. So now we've inserted the element, and now we have to update the tail. So now here's the problem that we were talking about before, where if we have multiple reserved elements here, we actually have to increment until they're all valid, while they're valid. Which means that our elements actually, we need a way of like marking them. So maybe we have a valid unsafe, we have a valid list of atomic bools of size n. Is that crazy? So here we can just keep moving forward while the elements are marked as valid. And the idea is that here we would write self.valid push idx store. This is going to be a store of true, and with ordering release, because this is going to have to be consistent across threads. And what's going to happen here is, now that we've pushed the element, we've marked ourselves as valid. Now we're going to say, while we move through our pushed index to reserved, so we'll say, we're going to like increment push index, up increment. And we're going to keep incrementing it until we've run out of valid elements, and then bump the pointer up until that point. And if two threads are doing that at once, that might be a problem. I guess we'll just have to make sure that both all threads that are doing this are not going to push it past too far. Okay, so we're gonna say let new tail, or let the tail is going to be we're gonna load the tail with ordering acquire. We're going to try to increment the tail. So we're going to say if next tail is going to be a wrapping increment. So we're going to say let next tail is a wrapping increment with size n of tail. And then what? We're going to say if self.valid next tail, we're going to load it with ordering acquire. We're going to try to increment the thing. So we're going to say self.compare. We're going to say what? Self.tail compare exchange weak. Push. The next thing is going to be the current is tail. Next is next tail. And we'll use the same ordering here. And if that succeeds, I guess it doesn't matter. If this succeeds or fails, we're still just going to loop again and read it back. So we actually just say, let's discard the result of this compare exchange, I think. Whether this succeeds or fails, we're just going to keep moving until valid is false. Else we break. And we can rearrange this actually to do the break here. And then this guy doesn't have to be an else. Okay, so we also have to check if tail is equal, if the reserved is hitting the head at some point. So we'll just say fix me handle reserved equals head. Wrap around. Very nice, very nice, very nice, very nice. So I think that this is probably fine. other than this fix me, I think that this will work. Now let's look at the pub function pop. He's going to take himself, and he's going to return an option t. And he's just going to check head and tail, right? So he's going to say, how are we going to mark this? Is tail going to be one passed? Tail's going to be the next valid. So yeah, we'll just say if head. So we're going to say if head is equal to self head tail. We return none. There's nothing to do. Which means that we're kind of committing ourselves to tail indicating one past, like the next valid. If they're equal, then there's no valid elements. Then otherwise, we're going to. So what happens if multiple people come in at once here? Let's think about that. What's kind of nice is I can probably ignore the multiple people popping at once case if I just say that this needs to be mutable. Right? This allows me... No, it doesn't. Shit. I was going to say that if I have one mutable reference for popping, then I don't have to handle the case where there are multiple people popping at once. But that's untrue because I wouldn't be able to push if I have a single mutable reference for popping. What I can do, though, is I can split out the pushing and popping into two different users. And if then I can only have one mutable reference to the pop side, I think that I can still get away with it. So I can get away with like not handling that case. So maybe what I'm gonna do is I'm gonna rename this Q class to like storage, and then what I'm gonna do is the sender and receiver are both going to have a reference to that storage. So we're gonna have like pub function or pub struct sender, and he's going to be a sender for T and N. And inside he's going to have storage. And this implementation of push is going to be for the sender. So we can actually say impl here. We just renamed this from storage to sender, I think. And for all of these self dots, we just say self dot storage. Just give me a sec, just changing all of these to storage. There we go. And great. Then on the receiver, which is the same type here, he's going to have a storage inside. And this actually isn't going to be a roster. This is going to be a reference to the storage. So we have to have a, or not a reference, a like shared pointer to the storage, which means that we need use alloc arc or sync arc probably. There we go. Right, it's gonna have storage like this. And now I can implement the receiver side. And here we're going to have a pop function pop. And this is going to take self by mutable reference, which ensures that we only have to worry about the case of one popper at a time. Great. So we're going to say, we're going to have that same if statement we had before, where if self.storage.head.load with acquire ordering is equal to tail with acquire ordering acquire. There we go. Nope, so this should be tail.load. We return none. Otherwise, we're unimplemented so far, and hopefully this compiles. Cargo check. I think that should compile. Yep. Cargo build. Yep. Great. And so what we want to do is what? We want to increment the head by 1 after we've loaded the data. So first we just get the data. Is self.storage.elements. Self.storage head. Here we have to do like a quick little dereference and get on this guy. We can say let head is equal to this load. And let me think for a second. Thinking. We'll write this here. Now, I'm actually starting to wonder if the head needs to be atomic. It's very possible that the head is only used from the receiver side, in which case we might be able to get away with it being non-atomic. I'll have to think about that in a second. Right, like maybe the tail and reserve. Yeah, let's... I mean, I didn't touch head in here. Oh, but I will later when I'm trying to deal with wrapping it with the collision of the head and the tail. So this is it does need to be atomic. So we'll say let data is equal to this unsafe block. This. We need a semicolon, and we need an equals here. At the end, we're going to return the data. This is now has to be head like this. Cannot move out of T and a non-copy array moves because of type T. Okay. So this actually gets a little more complicated, where these guys actually have to be maybe on init, right? Because what I want to do is I want to like take the element out and replace it with like a invalid element. But we can't do that. So maybe on init allows us to tell the compiler that we can put uninitialized shit in here and nobody will read it until it's initialized. Which means that we can use where's is it marker? Maybe on init. Where does this come from? Maybe on init. Mem. Of course. Which means here. What doesn't this like? Hold on. Cargo check. What's not compiling? Okay, everything's... Oh. Cargo build, maybe? There, it doesn't like that. Because it's found type parameter T. So I need to convert this into a maybe on init, which I guess is... how do I do that? Let's look at this maybe on init shit. X dot right. So I put in here a right elem like this. There we go. And now what we do is we say let uninit is maybe uninit, right? We swap this data in. So we'll actually say data is uninit. And we core mem swap data with the head element. And the idea is that now we have this uninitialized shit in there, and we'll pull data out. Now, really, do we want to do a swap? No, because we don't actually care that this data gets set. We can like leave the original thing in there. It doesn't fucking matter. So maybe we should do like a core, I think it's mem take, and replaces dest. I want to like take without uninitializing. So let's look at like if there's like a way to just do that. Replace take, forget a line of maybe I can just like copy the data out. So I can say data is equal to self.storage.elements. Maybe I can't just do that. Let's just see. So let data is equal to this guy. No swap. We just get him raw like this. And we delete this bracket. Cannot move out of type, non-copy array. So what happens to maybe uninit on drop? Does it do anything? I don't know. I don't know. Assume init drop. Drops the contained value in place. If you have ownership of the maybe, you can also use assume init as an alternative. Can I like as bytes? No. I want to like just copy the data out. Which yeah, fuck it. You know what? We'll do the take version for now, even though I don't really like it. That's fine. Yeah, that's fine. Whatever, doesn't matter. There's probably some like extra overhead going on there, but I don't care. So we take the data out, and once we take the data out, we have to like update our head. So we'll say self dot. Let me think about this. So since we know that we're the only person that could possibly be writing head, we can avoid this like compare exchange loop. And we can say note head is guaranteed to only be modified by us, a single writer. And so we can just say from here, instead of loading, actually, we can just do a fetch add. Boom. No, sorry, we don't want to do that because we don't know if we have to increment yet. So here we'll just say that self.storage.head store head +1 ordering release. Okay, and is there any other track to do? One is that this head +1 is wrong. We need to do a wrapping increment. This. What else? What else? we have to handle the case where we're right now we don't handle a full array at all. That's going to be a problem. So we're just going to say fix me if buffer is full, we probably will have to do move tail instead of head or something. Not really sure. I can't remember how to implement that yet. And do I have to update anything else? I think no. I don't think I have to touch tail or reserved. Oh, I guess I have to set the valid to false. So self.storage.valid head store false with ordering release. And we'll probably want to do that before we increment the head. Great. Great, great, great. So now when people write, they'll have an invalid, they'll know it's invalid. And that seems like it's probably it. Well, not it. We have to handle full buffer. Probably. Okay, so we've decided here that if head equals tail, we are going to be empty. So that means, sure. Which means if head is not equal to tail, we have substitute. So what is the empty case is, hold on. Empty case is this. So we have x, 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 x everywhere. And we have head equals tail equals reserved at this. Then we insert 1. So head is here and tail is here. Now, what happens when we get all the way around? Right, like when we get to here, right, where all of these guys are full. This is obvious, right? Like here we have head, tail, like this. But then what do we do when we insert something here? Do we set like head and tail and reserve to like a sentinel value that says that they're like out of, it's too full? Or can we change the representation so that this doesn't happen? Right? Like say we set tail, sorry, this will be like this. What if we set tail somewhere else? So we could say that in the empty case, replace O with X. In the empty case, maybe our tail... So what are our two options? Our tail could represent the last valid element, or it could represent the first invalid element. So if we say it's the last valid element, here, tail is going to be a sentinel value. So either way, we need a sentinel value. Either we need it on the side where it's empty or when it's full. And so our sentinel value is going to be n. So let's think about which implementation is easier. Here we have tail is pointing off into the nether. Over here. And when we push, we then set tail to this. Tail to head. Seems simple enough. And when it's full, we don't have to do anything. It's already all handled automatically. And the only thing we have to do is when we empty it completely, we have to, on the empty side, we would need to put tail to the sentinel value. If we have this case where tail is... Oh, I guess we could do the same thing with head, right? We could say that tail is always pointing to the next invalid element. Or the next, sorry, tail is always pointing to the last valid element. Sorry, thinking. Thinking. I was going to say that we could have tail always point to the last valid element, but there are some cases where there are no valid elements, so that's not true. We could always have tail pointing to one before where to insert, but that doesn't really make sense. So I think tail always pointing to where we should insert, I think makes the most sense. I like that. And then when we are full, we would have the case where tail is just pointing to our sentinel value. So we actually just say this: if this is equal to n, when we're full, it's equal to n, and when we're empty, head is going to be sentinel, or head is going to equal tail. Head equal to tail makes sense. So that's great. Now we just have to handle the case where if wrapping add is equal to, if the next tail is equal to head, if the next tail is equal to head, then we have to set it's the sentinel value. Which gets a little confusing because now we have to worry about synchronization of the tail from the pusher and popper. Let's think about that. I think for now, maybe we just... What happens if we just allow ourselves to have one extra empty element all the time? No sentinel value. Just the maximum capacity actually has an empty one in between. Does that make our life any easier? Let's think about this. So what is the order of operations? We increment, reserved, oops, too large. If this is the case, then we give up. Great. Increment tail should always succeed because tail will always be less than reserved. And then when we increment head, we might have to put tail. We might have to put tail / reserved to old head. And that's only in the case where tail was already sentinel value. Right, that makes sense. Okay, so on push, we say that if the... this might actually fail. So here in the success case, we say everything's good, right? But on the failure case, we return an error. And the failure case is simple. The failure case is if push index is equal to n, we return error. We failed because there's nothing to we can't push. We're too full. Great. Now, in the case where we're sentinel value, we only have to worry about this guy doing writing, right? This guy's reading, sure, but he will only update here. So that means that we can, if self.storage.tail, is equal to the sentinel value, so if tail is equal to n, self.storage.tail.compare exchange week. No, we want compare exchange non-week. The current value should be tail. The new value should be head. Success is ordering acrel. And this is ordering acquire. Now, we are pretty damn sure that this should always succeed. Because we should, like, nobody else should ever be modifying this. So I'm going to assert that this is true, or else this is a bug. We should be the only modifiers of tail in this case. And in this case also, first we should get the reserved value. And here we should be pretty damn sure that reserved is equal to tail. Or reserved is equal to n, right? Because if the tail was at the sentinel value, then the reserved should definitely fucking be at the sentinel value. Great. And I guess thinking. Maybe we should actually be checking reserved. Fuck, that's annoying. Do we have to handle these separately? Because like if the tail was at n, we do all this stuff. But what if the reserved was at n and the tail wasn't? We need to move the reserved to head instead of having it at our sentinel full value. I think this is okay. Because what will happen is like everybody will be modifying like the tail until we get to the sentinel value of it. Maybe we pop stuff in between, but that's fine. Like we'll just have like a slight suboptimal use of our queue while that's happening. So I think that's okay while people are pushing. So here we should be damn sure that the reserve value is the same as the tail value. Great. And here we should also be certain that we're the only people modifying this. So we're going to assert that res is okay. And then we return the data. So now the only thing that we have to do is actually set reserved and tail to the sentinel value if we are at head. So we can say let head is equal to, we're going to get this one time at the beginning. Self.storage acquire load, sorry, with ordering acquire. Here we're going to say if new reserved is equal to head, new reserved is now going to be our sentinel value to say it's full. And then we have to check tail too. So we'll say that if next tail is equal to n or to head, next tail is equal to n. Great. And I think that's probably it. Oh, and then we have to handle popping that, which we did here. If tail is equal to n, we handled that. So this fix me's gone. All right. All right. So we can, now we have to like construct these guys. So we're gonna make our queues. We're gonna say like pub function channel of type T is going to return a pair of sender TN and receiver TN. And so now n is going to be a const. So we're going to make our storage, which is a storage like this. Elements is going to be a maybe an init array. Like this, an init array. Head is going to be an atomic usize pointing to the beginning. So is the tail. and so is reserved. Valid is going to be an array of atomic bools of invalid of size n. Oh, and these elements actually have to be an unsafe cell as well. Which way does this go? Elements is an unsafe cell, maybe on it. Great. I forgot a comma here. Atomic bool does not have copy. That's annoying. Rust array atomic. That seems to work. Okay. So here it's a you have to do false n map x is atomic bool new x. Okay, there we go. I didn't expect that to work, but that's cool. Storage. And oh, here we need to create our sender and receiver. So we'll say let sender tx is equal to sender storage, which storage is actually going to be a clone of the pointer. Rx is going to be receiver with storage. And we can just say txrx is our return. Receiver was spelled horribly wrong. So just drop that in there. And here the linter is telling me that I can do this, which is kind of fun. Very, very cool. Okay. So now we need to start writing like a few unit tests just to make sure that like ignoring all of the atomic shit, did we at least get like the business logic correct? So we're going to make a module that's only created in test. We're going to use our crate testing utilities. And we're going to use everything from this module. We're going to create a test called like test. Maybe we'll just copy the circular buffer test that we had, because these covered some of our like broken cases. We're going to say let txrx is equal to channel new. And maybe we'll type cargo test here and make sure that we're failing. Yep, okay. So here we're going to say tx pushback, 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 pushback. Great, and this has to be a channel new with I32.3, I guess. Cargo test. Use of undeclared crate or module channel. Okay, so why does D like this? Oh, because this isn't channel new. This is just channel. This. So push back isn't the right thing. It's called just push, I think. Yep. Okay. And what's happening? Our cargo test just isn't running for some reason. So let's completely disable this just to see. So cargo test. That's also not running. So why the fuck are... Oh, it's just taking a while to boot. Okay, sorry, my bad. So if we uncomment this test, does that pass? No. Index out of bounds. The length is 3, but the index is 3. So that's a good sign. We fucked up something. Let's see. So probably if we're not handling the case where push index is n, it is here. If push index equals n, if new reserved is equal to n is equal to head, new reserved is equal to n. Thinking. So here it's going to be this next tail. Oh. Here we shouldn't be writing valid on next tail. We should be writing valid on push index. Oh. I see. So this is actually on the tail incrementing side. If next tail is n, we need to fail here. So let's just make sure that if next tail is equal to head, break? Let me think here. Let me think. If next tail is less than n and this, or this, if next tail is equal to n, thinking, sorry. So we break if the next thing is invalid, or we've hit the end. Which means down here we should say that if next tail is equal to n, we break. We still have to update the tail to next tail, and here we only check the validity. If we, well, let's think. Are we off by 1 on our validity check? So what are we checking here? We're saying that if we have like a reserved slot and a tail slot, and if we are incrementing our tail and it's valid, then we're good. Or if the next tail is equal to head, that's the other case. So if it's not valid, we break. Or if it's head, we break as well, but not before writing it. Right. So here we just say if next tail is not equal to n and this. All right, that seems reasonable. I think that's right. Let's see. Okay, so that buffer full test now passed. This pop empty test now we can run it as well. So this is the same thing where we create this guy and we say tx.pop is not. So this is an empty pop. It should give us this should give us a none. So why is this not compiling? tx.pop, method not found in sender. Oh, rx.pop, my bad. Not tx. This needs to be mutable, of course. Obviously. Awesome content. Thanks, dude. We try. Now we have these like sequences of pushes and pops. So here we're going to say let tx mute rx is equal to a channel, not a circular array anymore, of i32.3. So we're going to push that we're okay to push. Then when we pop, we're good. We get the value back. And if we try to pop again, it's not. Cargo test. Let's see it. Okay, that doesn't work for some reason. We get 1 again. Oh, that's not good. That's not good at all. That means that we fucked up the logic of our head pointer. So how is that possible? We stored the wrapping increment of head. So maybe we just let's see. So head would then equal to tail. So let's take a quick look see here. First, let's just double check this log. So the log is at 187. And that's actually this. Oh, I see. So after we push our first element, the pop does not get it for some reason. So that makes more sense. So here we have head is equal to this and tail is equal to this. So let's just print head and tail. And see what comes out. So here we'll just say print line, head is this, and tail is this. I forgot a comma. So let's just quickly check this. And so head 0, tail 0, head 0, tail 0. So in both cases, after a push, at 189, he doesn't get something. So that's a little good. Oh, I guess this is the first time that we've tried to read back what we wrote in our test. So that makes sense that this is failing. So the tail just never incremented, it looks like, after the push. Probably, so here we set valid on the push index. And it's because we're checking the wrong index of tail. This should be checking if tail has valid. Right, because like we have the tail is pointing to the next place that we could write to. So I think that's reasonable. Let's cargo run again. Oops, not cargo run, cargo test, my bad. Okay, and so now that test is passing, great. And we're gonna test this full, then not full case as well. So this comes from our circular array test as well. So we have let tx and mute rx is equal to channel i32.3. So here are all these buffer.pushbacks. So we say replace buffer pushback with tx.push. And we say replace buffer.pop front with rx.pop. And cargo test. Okay, so we have some problems in here. So where is this? Assertion failed, res is okay. Oh, that's interesting. So here we fill up the thing and we do our first pop. And here we are failing on one of these. So does it tell us which line our assertion is failing at? No. So we'll just write down print line hello 1 and hello 2. And it's the second result is okay. So for some reason, this compare exchange of reserved to head is not working. So why? Oh, because this is tail, not reserved. Oops. That's good. Assertions saved the day again. Look at that. Very nice. Okay. So all of our existing tests from our circular buffer stuff ported over to our new lock-free queue, those are all passing now. And that's good news. I'm gonna quickly read over this one more time. I'm concerned that this valid stuff that I might have made a mistake there related to the reserved side as well. So I'm just gonna read over the reserved stuff again one more time. So we have a push index, which is our where in our array we're ready to start writing data. If it's a sentinel value, we say fuck that with nothing to do. We return an error. Otherwise, we try to make a new reserved, and if the new reserved collides with the head value that we had at the beginning of the push function, then that fails. Great. Then we try to reserve it with an atomic exchange. That looks sane. We write the element in, and then we say that it's valid. Then we try to update the tail. Yeah, okay. That all seems sane. I think that there's a good chance that there's a bug in here, a very good chance. Right, this shit's hard to get right, but it kind of seems like it's working at least in single-threaded code, and it's behaving semi-sanely, which is pretty cool. So let's implement sync for receiver of t and n. This is for and I guess this is not for all t's and n's. This is only for t's and n's where t implements send, I think. Maybe it is for all T's. No, that's fine. That's fine. Because the sync, like, T is only ever going to be accessed from a single thread. There's a send thing going on here. T needs to implement send for this to work correctly, I think. But we'll think about that in a second. So we have Tn, where n is a const usize. And I'm actually concerned, now that I think about it, there's like a handoff between threads. And I don't know if we might need a memory, like a full-on memory barrier there. So somewhere in our pop, we need like a stronger guarantee of ordering here. So our head, we actually might want this to be seek syst. Probably this one actually. So here, use seek syst ordering to force all actions for tail movement to be synchronized. Right, I think that's what I read in these docs here, where I have seek syst. With the additional guarantee that all threads see sequentially consistent operations in the same order, which was not very clear, but in the C++ version, it says not only order memory the same as acquire release ordering. Everything that happened before is stored in thread. Oh. Never mind. I think the guarantee here for acrel might. All memory writes that happened before the atomic store from the point of view of thread A become visible side effects in bed B. Okay, never mind. This is totally fine. Acquires good enough for us. Okay. Okay. So overall, that looks okay. We have a sync implementation. And let's just add this now. And we'll say git commit -m first attempt at lockfree queue implementation. And this is at 1:27:20. And now let's try replace logger queue with async queue with lockfree. And this will give us some indication about whether or not we've like heavily fucked up to the point where it won't work. This will just give us like some like API checks and stuff. So let's go to our logger. And here, let's think about this. We'll have a, instead of just having our logs here, we're going to have a log tx, which is going to be a sender from our lockfree queue. Fuck, my fucking language server crashed, so let's just quickly restart my editor. We'll go back to the logger. And what? We have a log tx, which is a sender of logs with size 1024. And log rx is a receiver of log 1024. Now our log service loop, the part who's like reading the logs, he needs mutable access, but two, he can use a mutex because we're only using the sender side from interrupts where it's dangerous to use mutexes. So here we can say async mutex here. Here our logs are no longer like this, and our service loop looks like actually, we don't even need the mutex here. We can use something with like interior mutability. So we can actually say RC receiver. Nope, we'll use mutex so that he can be like synced between multiple threads. So we'll say let tx_rx is equal to lockfree queue. So here we need to include ourselves. And we'll say lockfree queue channel. Great. We have our lock-free tx and rx. And this is going to say log tx and log rx. We'll say let log rx is mutex new log rx. Great. And now here we can just say log rx and log tx as our elements in our logger. Wonderful. This is kind of fucked because this is a const function, so that means that we actually have to go into our lock-free queue and make sure all of this stuff is const as well. So the channel creation, we can just say pub const function new probably. I don't know if this is gonna let me. It looks like there's no errors there, which is great. But we're on like maybe that comes at like a later stage of compilation failures. Let's cargo check and see what it's bitching about. So unsafe cell, uninit, blah, 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 cannot be shared between threads safely. So I have to implement this for the sender as well. The sync thing. Now I don't understand what it's mad at. Unsafe cell, receiver. Unsafe cell doesn't appear anywhere in this logger stuff. Am I crazy? Unsafe cell usize cannot be shared between threads safely. Which one of these many things is upset about? Unsafe cell, lock-free queue receiver cannot be shared between threads safely. Why not? Because unsafe cell doesn't implement sync, but am I high? What am I missing? This is like not a type that shows up anywhere. Right? Because it appears within the type mutex receiver. Oh. Because my mutexes aren't fucking synchronized either. Oh, god damn it. Okay. So... Oh, that's fucking annoying. Yeah, that makes sense. That makes sense. For now, we're just gonna say unsafe impulse sync for mutex because we're still assuming a single thread OS. We'll come back to this later. And we'll say, note, assuming single threaded OS. Right, this is just like one of the many problems to solve now. Cargo build. Okay, so now we have this issue where like this is not how we wait anymore. So we have self.logs goes into our log waiter. And this should be log rx probably. So this guy is going to take log rx and he's going to take a mutex receiver instead of a circular array. And here we're going to have log rx.lock.pop. Great. We need to await the lock. No. We need to pull the lock. So we're going to say, we're going to try to lock it. So we're going to say let guard is equal self dot log rx dot lock dot pull cx. We need to pin it. So we can say or pin, I think, in here. Yep. CX now needs to be passed on. And we say, if the guard is not ready, we're not ready. So we say match guard. And we say if we're on like whole ready v, we just return, we propagate the value. Otherwise, we return poll pending because our mutex isn't ready. Great. Now we try to pop the value for the guard. Okay. No method named pop in guard. What the fuck? The guard is a poll. Oh, oopsies. There we go. And this guy needs to be mutable. Great. And now I think that's working. And now we have the like service side is good. But on the push side, we'll have, instead of trying to write to the buffer directly, we have a log tx, just as a push. There we go. Shit, we can't construct this guy in a const context anymore, which means that we can't like statically initialize him. Oh, which means that we're gonna have to do some like logger initialization stuff. So how do we do this? Our logger. I guess we'll just put these things as options. Is that correct? How do we initialize these later? Let's think about this. I think we can do something like, say, pub struct logger holder, which takes in a logger, and we'll say unsafe impl. This is going to take an unsafe cell to a logger. And we'll say unsafe impl sync for logger holder. We'll use core cell unsafe cell. So the idea is that we want to be able to initialize our logger in static memory with like one mutable reference one time. Which is going to be annoying, but that's okay. And maybe we'll call this a maybe uninit. No, yeah, maybe uninit logger, which also needs this like mem maybe uninit thing. So now this logger is going to be a logger holder, which is going to be a unsafe cell new maybe uninit. Does this work? Like this, logger holder. I don't know if this is going to let us make these in with constants. That seems okay for now. Okay. Now we need in our main function, when we service our logger, where do we get our logger from? Oh, we call this logger service. Perfect. So here, our logger now is a thing that has a thing inside. So we'll say .0 get. Is get correct? Let's look at the docs for unsafe cell. Is there a way to like just use him normally? Gets a mutable pointer to the right value. Get gets this thing into inner. Is there like a deref implementation? No. Okay, so I just call get on him, I guess. And so I say logger.get .service. Probably like star this and 0.service. Sorry. Logger.get. This is going to be the unsafe cell. No, this is going to be the maybe uninit. So does assume init not work here? Oh, I need the .0.get. There it is. And so now I have assume init ref .service. There we go. And probably await here. Great. Great. Now here we have to do something very similar probably. We have logger 0.get assume init. Oh, here we have to set the values. So here, instead of just creating the log levels, we're actually going to create the whole fucking thing. Right, so here we can get rid of this option shit, and we can say logger.get is equal to maybe it's like dot write logger new. Nice. So this is how we initialize it, I guess. And then we can say logger.0.get assume. We assume init mute, and we write the levels as the levels we got passed in. Fantastic. Fantastic. So this is a hash map new here now. Here we can back out a bunch of stuff. And now we have all these like push log things. So this now is like self.logger .0.get .assume init ref or something. Jesus Christ. Cool. And now I guess because these are macros, this actually has to be like totally public. Great. And I do the same thing here. No method called get level, so we need to do the same shit here. So we say .0.get level. Assume init ref. Great. Great. And this probably all has to be like in an unsafe block now because this is using some like unsafe cell shit. And we do the same thing here. So we wrap this in unsafe. And this guy has get level, so we need to do this like we dereference the pointer that we get, and we assume init ref. We put a .0 here. All right, cargo check. Do we compile now? We're close. Our lockfree queue had tried to make a const function that we don't need anymore, so we'll just delete that. Async mutex at 45 has a non-const function. Okay, but we're not trying to be const, so we'll just write that as well. Okay, we're running. Let's run our thing. And hope to God we get some logs. Okay, we got one log. Then a bunch of stuff isn't working correctly. So that's interesting. That's very interesting. So let's think about why that would be. So here we'll print line the log as we push it. So this is log. So here, pushing the logs immediately, they're getting pushed in, but they're not getting popped out. So it could be this log waiter problem. Or it could be a problem with like the thing we're working with. So how can we test this? We can say print line waiting. And if we see this only one time, then there's a problem. Right, so that's a problem, is that waiting is happened a few times. Let's try just never servicing the loop. So we'll just say, we'll go to main and we'll look for our logger service. And can we just not do that? So we can just do this instead, maybe. And if this performs good, then we're good. But this looks like this is also not performing correctly, even if we're not running the logger at all. That's interesting. So maybe in our logger, this like unsafe cell shit, maybe we've like made a mistake. Yeah, not sure. There must be some sort of form of like invalid memory access going on. And it must be related. I would guess that it's related to this static bullshit that we were just doing. But how could we test? So let's here print line the log again. So if we print the log immediately, we actually seem kind of fine, right? It's weird that now we're getting more weightings versus here, where we only get a few. So without changing what's going in, that's a good sign. It could be that the log waiter is not doing what we want it to do, so let's take a look at this. Let's double check. I don't think that this should ever be pending. So let's throw an assertion in there just to check. I think that like since we only have one person servicing the loop, we should never fail. Great. That's a good sign. And so now it looks like we're not getting values out sometimes. So maybe what we should do here is instead of asserting there, we'll print that we return pending. And maybe we'll do it here too, just for sanity. So this is print line pending 2. So weirdly, our whole OS is like locked up for some reason. That's weird. Let's look at that again. Okay, so first of all, pending 2 is getting spammed, but not with a new line. Why the fuck not? Something's locking up. Something's locking up. So like the whole OS is like doing something stupid. So maybe let's remove the push side and see if the OS is still frozen. Yeah, there's something. Look at this shit. Like, why is it just like typing out characters to the screen? So I wonder who could be fucking that up. It would be nice to like get GDB up and running. I guess let's also who else can we, if we don't service here. Oh, oops, that's a let's change this to a join real quick so that we don't immediately exit. It does seem like even without interacting with the lock-free queue, we've got some like weird shit going on. So I'm going to assume that that's related to maybe this guy. Like this like attempt to stick this guy in like static namespace maybe is causing problems. So what if we did cargo run without release? Like disable optimizations. They were also failing in a weird way. Okay. Okay, so let's try getting rid of the initialization and the service. Let's just try like getting rid of like everything, right? So we'll just say that like calling get level doesn't interact with memory, calling push log doesn't interact with memory, calling loop doesn't interact with memory. Let's just like disable the logger completely. Let's say log level error or something, just like so that it returns something. So that does, so okay, that's good. It is related to like interacting with the logger or with the, yeah, logger memory and static memory. Changing the get level to pull from the module is okay. Is it when I initialize? Is that causing problems? That definitely looks like it's fucking us in some way. So that's a good sign. So this must not be valid like I thought it was. So I have this logger, unsafe cell new, maybe uninit new, and writing a new logger is causing issues here. I wonder why that would be. Where is my logger initialized here? Right after my allocator with interrupts off. Great. I'm not seeing it. I'm really not seeing it. So I have this unsafe cell, which I thought should be safe to put here in static memory. Where's my logger holder definition again? And the only places I'm assuming it's initialized is after I've written it, right? Because the init comes very early. Unless in my allocator, I'm trying to log. But there's no way. Info. Yeah, I don't see any use of the logger in the allocator, which is good. Yeah, I'm really not seeing it. I don't understand why just calling logger initialization is triggering this fuck up, unless it's undefined behavior to put this like unsafe cell, maybe on init, in here. Is it this? If I like don't initialize my log levels, does that still cause shitty behavior? Yeah, very odd. Very, very odd. I guess it could be that this mutex is using interior mutability and static namespace and can't like move around or something. Could be the lockfree queue. Yeah, I'm not seeing it. Not seeing it. Okay, I'm going to take a break. Come back at this with fresh eyes tomorrow. But I think that like I'm pretty sure that at the very least our lock-free queue implementation seems pretty damn sane. I was hoping to prove its value on the logger, but I'm struggling there. There's something else going on, I think, with invalid use of static memory. Initialization of this thing is getting a little harder now that we have some more complex initialization that needs to be done. So, yeah, I think that we'll come back at this tomorrow. Thanks for watching. If you like what you saw, you can always tune back in most days at around 1 p.m. Pacific time on Twitch. And if you're not watching on Twitch or you miss a Twitch thing, you can watch on YouTube. Twitch or YouTube is linked in the Twitch description. And if you're on YouTube and you want to pop in live, feel free. Thanks for watching. Catch you on the next one. Bye.